All right, for part B, I'm going to utilize the power series of arctan(x) that I derived in part A, right? So we're going to sort of like use this towards here, and I need the power series of x squared arctan(x) because that's what we have in the integrand for part B. So here we go. Let's write x squared arctan(x) here. So I'm going to multiply the power series of arctan(x) term by x squared. So I'm going to carry forward minus 1 to the n. X squared times x to the 2n plus 1 is x to the 2n plus 3, and all divided by 2n plus 1. All right? So once we have it, we can go ahead and integrate the power series, because what I'm going to do here is to replace x squared arctan(x) in the integral by the power series here. Okay, so here we go. Integral from 0 to 1/2, the summation minus 1 to the n, x to the 2n plus 3 divided by 2n plus 1. Let's put everything in parentheses and, and integrate term by term. Okay, so let's see what we get. The integration is like term by term, so so minus 1 to the n stays here. I'm going to add 1 to the power, so then you have x to the 2n plus 4, and I'm going to divide by that power, and I also had 2n plus 1 back down here. Okay, so that's good, and I need to evaluate this at the lower limit and at the upper limit. Okay, 0 and 1/2. So that means that in the next step, I'm going to plug in 1/2 for x. So let's just rewrite that infinite series again. Minus 1 to the n 1/2 to the power of 2n plus 4, and the same bottom. What's good here is that the lower limit spits out 0, because the very first term here starts with, for n equals 0, starts with x to the 4th divided by 4. Right? This infinite series is starting with x to the 4th divided by 4 and going all the way forward, right? And when you plug in 0 for x, and that is going to spit out 0. So the lower limit is just providing you just 0. And here we got another alternating series, and you can use the alternating series remainder theorem. So Rn, the error, the amount of error, is approximated by an plus 1. Let's say like I cut the sum at the second term, so then R2 is going to be estimated by a3, okay? And I want this to be less than 10 to the minus 3. Okay, so an plus 1 to be less than 10 to the minus 3. All I'm going to do next is just to list a few terms in the infinite series, and then whichever term is giving me less than 10 to the minus 3, I'm going to stop, and I'm going to take the summation of the terms before that term. So what I mean by that is if you list the sum for n equals 1, so you get 1 over 64 minus 1 over 1152. So this is the very first term, this is the very second term, okay? And turns out that this term here is less than 10 to the minus 3 already. So I'm going to make my estimation based on only one term. So essentially that integral, let me just rewrite that integral from 0 to 1/2 x squared arc tan x dx, okay? X squared arc tan x dx is approximately equal to 1 over 64, and if you want, you can use your TI-84 to say that this value is closer to 0.016. Okay, this is sort of like how we implicitly use the alternating series remainder theorem to estimate the value of this integral. So power series are not just like used to estimate function values, but in the meantime, integral values as well. All right. All right. So this ends the video. Thanks for watching. I'll see you in another video. Bye.